Hey everyone, welcome. Today, we're tackling a Leetcode problem called Count Good Triplets in an Array. It sounds a bit abstract maybe, but don't worry, we'll break it down step by step and figure out an efficient way to solve it. Ready? Let's dive in. Okay, so what's the deal here? We're given two lists of numbers, let's call them nums1 and nums2. Both lists contain the same numbers, from 0 up to n-1, just possibly in a different order. They are permutations basically. Our goal is to find good triplets. A good triplet is a set of three distinct numbers, say x, y, and z. These three numbers need to appear in increasing order in both lists. So if we find where x, y, and z are in nums1, their positions must be increasing. And if we find where x, y, and z are in nums2, their positions also need to be increasing. We need to count how many such triplets, x, y, z, exist. The constraints tell us the lists can be pretty long, up to 100,000 elements. So, we'll need something efficient. Let's look at the first example. nums1 is 2, 0, 1, 3, and nums2 is 0, 1, 2, 3. We need triplets, x, y, z, that appear in increasing position order in both. Let's test the triplet, 0, 1, 3. In nums1, 0 is at index 1, 1 is at index 2, and 3 is at index 3. Yep, 1, less than 2, less than 3, the positions are increasing. Okay, now check nums2. 0 is at index 0, 1 is at index 1, and 3 is at index 3. Yep, 0 less than 1 less than 3, positions are increasing here too. Since it works for both lists, the 0, 1, 3 is a good triplet. The example says this is the only good triplet. Let's see why 2, 0, 1 isn't good. In nums1, 2 is at 0, 0 is at 1, 1 is at 2. Positions 0, less than 1 less than 2. Okay, so far. But in nums2, 0 is at index 0, 1 is at index 1, and 2 is at index 2. The order of values, 2, 0, 1, gives positions 2, 0, 1. Since 2 greater than 0, the positions are not increasing in nums2, so 2, 0, 1 fails. Makes sense. We need that increasing position order in both arrays. So what's the most obvious way to start? Well, we could just generate every single possible combination of three distinct numbers, x, y, z, from 0 to n1. For each combination, we'd find their positions in nums1 and check if they are increasing. Then, we'd find their positions in nums2 and check if those are increasing too. If both checks pass, we count it. But how many triplets are there? If n is the length of the lists, it's roughly n combinations, or big O of n cubed. Given n can be up to 100,000, n cubed is way too big. That approach will time out for sure. We definitely need a smarter plan. Okay, let's rethink. Instead of picking three numbers and checking, what if we iterate through the first list, nums1, and focus on each element as a potential middle element of a triplet? Let's say we're looking at the element y equals nums1 at index j. For y to be the middle of a good triplet, x, y, z, we need two things. First, we need an element x that appeared before y in nums1, so x equals nums1, with I less than j. Second, we need an element z that appears after y in nums1, so z equals nums1, with k greater than j. And crucially, their positions in the second list, nums2, must also be in increasing order. Let's write pos2v for the index of value v in nums2. The condition becomes, we need pos2x less than pos2y and pos2z greater than pos2y. So for a fixed middle element y at index j in nums1, we need to count how many elements x came before it, I less than j, and satisfy pos2x less than pos2y, and how many elements z come after it, k greater than j, and satisfy pos2y. If we can count those efficiently for each y, we might be onto something. Since we constantly need to know the position of a value in nums2, let's make that look up fast. We can create a map, let's call it pos2, where pos2, the uenses state, gives us the index where value appears in nums2. We can build this map once at the beginning, by just iterating through nums2. For example, if nums2 is 4, 1, 0, 2, 3, our map would store 4 is at index 0, 1 is at index 1, 0 is at index 2, and so on. This way, whenever we have a number, say y, we can instantly find its position in nums2, using pos2. This will be super helpful. Okay, let's put it together with our pos2 map. We'll loop through nums1 using an index j. The number at this position is y equals nums1. We find its position in nums2 using our map. Target underscore pos2 equals pos2. Now for this specific j and y, we need to count two things. First, left underscore count. How many indices I before j, so I less than j, have the property that the number nums1 appears in nums2 at a position smaller than target underscore pos2. That is, po is 2, nums1 less than target underscore pos2. Second, right underscore count. How many indices, k after j, so k greater than j, have the property that nums1 appears in nums2 at a position larger than target underscore pos2. That is, pos2, then chums1, greater than target underscore pos2. If we find these two counts, left underscore count and right underscore count, for our current y, then any combination of a valid element and a valid element forms a good triplet with y in the middle. So the total number of good triplets using this specific y as the middle is simply left underscore count multiplied by right underscore count. We do this calculation for every possible middle element y by iterating j through nums1 and add up all these products to get the final answer. The challenge now is how to find left underscore count and right underscore count efficiently. This is where a cool data structure called a binary indexed tree, or bit, sometimes called a Fenwick tree, comes in handy. What's it good for? Imagine you have a list of counters, initially all 0. A bit lets you do two things very quickly. First, you can increment the counter at a specific position. Let's call this update. Second, you can ask, what's the sum of all counters from the beginning up to a certain position p? Let's call this query. Both of these operations, updating and querying the prefix sum, take only log n time, where n is the size of the range the bit covers. This is much faster than just using a simple array, where updating is fast, but getting the prefix sum would take linear time. This sounds promising for our counting problem. So how do we use the bit? We'll create a bit that can handle indices from 0 to n1, representing the possible positions in nums2. As we iterate through nums1 with our index j, let's say we are looking at the value y equals nums1. We find its position in nums2, which is target underscore postdidist equals postdidist2. Now before we do anything else, we use the bit. We query the bit for the prefix sum up to target underscore post2 Since the bit is storing counts of the post2 values we've already encountered for I less than j, this query bit.query target underscore post2 directly gives us left underscore count. It tells us exactly how many elements processed before j had their nums2 position less than the current element's nums2 position. Cool. Okay, what about right underscore count? We'll get to that. After we've calculated both counts for index j, we then update the bit by adding 1 at index target underscore pos2. This signifies that we have now processed an element whose nums2 position is target underscore pos2. Now for the slightly trickier part, calculating right underscore count. Remember, right underscore count is the number of elements z that come after index j in nums1, so k greater than j, and have pos2 greater than target underscore pos2. How can we find this using our bit which only knows about elements up to index j? We can use a little bit of subtraction. First, how many numbers in total from 0 to n1 have a position in nums2 greater than target underscore ps2? Well, there are n positions, 0 to n1. The positions greater than target underscore ps2 are target underscore ps2 plus 1. n1. The count is n1. Target underscore ps2 plus 1. Plus 1, which simplifies to n1. Target underscore ps2. Okay. Now from this total, we need to subtract the ones we've already seen. Indices I less than equals j. That also satisfy pos2. 1 greater than target underscore pos2. How many of those have we seen? We've processed j plus 1 elements total, from index 0 to j. How many of these seen elements have pos2 less than equals target underscore pos2? We can get this from our bit before we update it for j. It's bit.query target underscore pos2. Wait, let's use left underscore count, which is bit.query target underscore pos2 to 1. The number of elements seen with puck2 equals equals target underscore part2 is 0, before we update. So the number seen with part2 equals 2, greater than target underscore part2 equals 2, is j, left underscore count. Therefore, right underscore count is the total possible count, minus the count we've already seen, n, 1 target underscore pos2, j, left underscore count. Phew! That gives us the count for elements yet to come. Okay, let's summarize the full plan. First, create that handy pos2 map that tells us where each number lives in nums2. Second, set up our binary index tree, let's say of size n, filled with zeros. Third, initialize our answer, the total count of good triplets, to 0. Fourth, we loop through nums1 using index j. Inside the loop, find the current number y and its position target underscore pos2 in nums2. Use the bitty to query the sum up to target underscore pos2 to 1, that's our left underscore count. Calculate the number of elements we've already seen whose position in nums2 is greater than target underscore pos2. We found this was j, left underscore count. Calculate the total number of elements that should have a position greater than target underscore pos2, which is n, *1, target underscore pos2. Subtract the ones we've seen from the total to get right underscore count. Add the product left underscore count, right underscore count to our overall total. Finally, and this is crucial, update the bit by adding 1 at index target underscore pos2 to record that we've now seen this position. After the loop finishes, the total count holds our answer. We just return it. Alright, let's look at some code. First, we need the binary index tree itself. Here's a typical Python class for it. The __init___ method creates a list, usually one element larger than the maximum index we need, filled with zeros. Notice it uses one-based indexing internally, which often simplifies the bit logic. The update method adds a, usually 1 for counting, to a given index. It converts the 0-based input index to 1-based, and then repeatedly adds the delta to the current position in the tree, and moves to the next relevant index, using that bitwise trick index plus, equals index and index. The query method calculates the prefix sum up to a given 0-based index. It also converts to 1-based, then loops, adding the tree value at the current position to the sum, and moving the tree using index, equals index, and index, until it reaches the start. This gives us the sum or count from the beginning up to the requested index. Now, here's the main part of the solution using that bit class. We first get n, the size of the arrays. Then we build that pos2 map to quickly find the index of any value in nums2. We create our bit instance of size n. And we initialize our total underscore good underscore triplets count to 0. Then comes the main loop, iterating j from 0 to n1. Inside we get the value y equals nums1, and its position target underscore pos to 2 using the map. We calculate left underscore count by querying the bit up to target underscore pos to 2 to 1. Then we calculate right underscore count. As we figured out the total number of values that could come later with a pos2 greater than target underscore pos2 is n1 target underscore pos2. The number of values we've already seen before index j that have pos2 greater than target underscore pos2 is j left underscore count. So, right underscore count is the difference. n, 1 target underscore pos2, they, left underscore count. We multiply left underscore count and right underscore count, and add it to our running total. Finally, after using the current target underscore pos2 for calculations, we update the bit at target underscore pos2, marking it as seen. Once the loop finishes, we return the total count. So how efficient is this approach? Let's look at the complexity. Building the pos2 map takes time proportional to the list size, so that's order n. The main part is the loop that runs n times. Inside the loop, the most expensive operations are the bit query and the bit update. Both of these take log n time. Everything else inside the loop is constant time. So the total time is roughly n times log n, which we write as big O of n log n. This is much faster than the n-cubed brute force, and it should be well within the time limits for n, up to 100,000. What about memory? We store the pos2 map, which takes order n space. We also store the bit's internal tree, which also takes order n space. So the overall space complexity is order n. Alright, let's quickly recap the main points. We needed to count triplets whose values appeared in increasing position order in both input arrays. The brute force check was too slow. The key insight was to iterate through the first array, focusing on each element as a potential middle element y. We used a mapping to easily find the position of any number in the second array, pour true. Then, the core trick was using a binary index tree. As we processed each y, the BIT helped us quickly count how many previous elements x satisfied the position condition, the Poneg using condition. We called this left_count. We then used some counting logic, combined with the BIT's information about elements seen so far, to figure out right_count, the number of future elements z that would satisfy post 2, greater than post 2. Multiplying these counts for each y and summing them up gave the final answer, all done in efficient n log n time. Hope that explanation made sense and helped you understand how to tackle this problem using a binary index tree. If you found this useful, please hit that like button, consider subscribing for more Leetcode breakdowns, and feel free to leave a comment if you have any questions or other approaches. And hey, if you're feeling extra supportive, the Boba Fun link is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.